We're on problem 207. If n is equal to 4p, n is equal to 4p, where p is a prime number greater than 2, so p is prime and it's greater than 2, how many different positive even divisors does n have, including n? So how many integers go into n, or go into 4p? Well, definitely 4 goes into it, right? Because this is going to be a multiple of 4. And then anything that goes into 4 will also go into it, so 2 goes into it. 2 is also a divisor. P would go into it, right? And are there any other numbers that go into P? Well, no, P is prime. Well, 1 goes into P. But they wanted to know, they wanted to know the different positive even divisors. So the positive, we're just dealing in the positive world. That just lets us know this isn't some trick question where we have to count negative numbers. But they want even divisors. So first of all, 1 is not even, so that can't be it. The second question is P even. Well, by definition, if P was even, and if it's greater than 2, it would be divisible by 2, so it wouldn't be able to be prime. But they tell us that P is prime. And P is prime and it's greater than 2, so it can't be divisible by 2, so it has to be odd. So this is also not an even divisor. So there's only 2 even divisors, 4 and 2, so the answer is 2A. Problem 208. 208. S is a set containing 9 different numbers, so S has 9 numbers. T is a set containing 8 numbers. T contains 8 numbers, all of which are members of S. Okay. Which of the following statements cannot be true? The mean of S is equal to the mean of T. So let's think about this a little bit. Let's say, so choice A, that their averages are equal to each other. Let's just say that set S is equal to 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so what would its mean be? Well, its mean, if you average all of these numbers, if you average 1 and 9, you get 5. You average 2 and 8, you get 5. You average 3 and 7, you get 5. You average 4 and 6, you get 5. You average 5, you get 5. So the average is 5, right? So so if this is S, and what if T were this? What if T were just this right here? So let me label that. That's T. And that's not 7, that's T. And then S is everything. So it's T plus the 5. So the average of all the numbers in T, if you average 1, 2, 3, 4, 6, 7, 8, 9, your average is going to be 5, right? I mean, think about it. The average of 4 and 6 is 5. Average of 3 and 7 is 5. I think you get the idea. You could work it out if you like. And then if you were to take set S, which is all of these numbers plus the number 5, if you add 5 to a set of numbers whose average is 5, the average is still going to be 5. So A definitely works. B. The median of S is equal to the median of T. Well, once again, that's true with this set. This is a good set to work with. It proves everything we need to prove. What's the median of T? It's the middle number in T. There's 8 numbers, so you have to average the middle 2 numbers. So if you average the middle 2 numbers in T, 4 and 6, you get 5. So 5 is median of T. And then what's the median of S? Well, now S includes the 5, so you can put all of these numbers in order. And so 5 is the middle number. So 5 is also the median of S. Choice C. So both of these can happen, A or B. Choice C. The range of S is equal to the range of T. So the range of a set is just the difference between the highest and lowest number. And then the range of S is equal to what? The highest number in S is 9. The lowest number in S is 1. So that equals 9 minus 1, which is equal to 8. What's the range of T? Well, the highest number in T is 9. The lowest number is 1. 9 minus 1 is equal to 8. So this one can definitely be true. Statement D. The mean of S is greater than the mean of T. Well, sure. Instead of this being a 5, what if this was a 50? Right? Now all of a sudden, the average of T would still be 5, but if you throw this 50 in there for S, your average is going to go a good bit above 5. So statement D could definitely work if you just make that extra number that's in S a lot larger number. And then statement E, which I'm guessing is the choice that cannot be true, because we could figure out a case for all of A through D. The range of S is less than the range of T. The range of S. So the range is the difference between the highest and the lowest, right? So the range, no matter what, the range of S has to be at least as large as the range of T. Think about it. In this case, the range of T is 9 minus 1, which is 8, right? So you could make the range of S larger if you used 50. If 50 was the extra number, then the range is 50 minus 1. But considering that all of these numbers in T are also in S, the difference between the highest number in T and the lowest number in T has to be less than or equal to the range of S. So they're saying the opposite. The range of S is less than the range of T. And we know this cannot be true because T is a subset of S. So the choice is E. Next problem. Took me more time than I wanted to. 209. How many different positive integers are factors of 441? Well, they are essentially just at factoring it. Well, let's see. This should be divisible by, let's see, 4 plus 4 is 8, plus 1 is 9. So this should be divisible by 3. So 3 goes into 441. 1 times 3 is 1. Bring down to 4, goes into 4 times 12. And then you get 21, 27. Right. So you get 3 times 147. 3 and 147. And then 3 should also go into this, because 1 plus 4 plus 7 is 12, which is divisible by 3. So 3 goes into 147. 147, you go 4 times 12, 27, 49 times. So let's just do a prime factorization of 441. You get 3 and 147. 147 factors into 3 and 27, which then factors into 3 and 9, which then factors into 3 and 3. Okay, so I didn't realize, but this is a lame, that this is the same thing as 3 to the 5th. Is that right? 3 times, is that, 3 goes into 140, oh no, sorry, I made a mistake. 3, let me redo this. 3 goes into 147, not 27 times, 49 times. So then this is, if you do prime factorization, a 7 and a 7. Right? I was about to say 441 isn't 3 to the 5th power. So let's write that down here. So 440, let me do it in a different color because I don't want to be confusing. So 441 is equal to 3 times 3 times 7 times 7. Right? So if they want to know how many different positive integers are factors, so all you have to think about is how many positive integers can I construct with 2 3s and 2 7s. So let's just list them. 3 definitely works. 3 times 3 will definitely work. Well, let's go in order. 7 will definitely work. 3 times 3 will work. That's 9. 3 times 7 would work. 21. 3 times 49 will work. Right? 3 times 7 times 7. So 3 times 49 will work, which was actually 147. 147 works. Then 9 times 7 would work, which is 63, right? 9 times 7. And then you have 9 times 7 times 7. So that's essentially 441. Let me make sure I haven't missed any combinations, right? You have 1 3 and 1 7. So you have a 3 and a 7. You have a 3 and 2 7s. You have 2 3s and a 7. 2 3s and a 7. And then you could have 2 3s, 2 3s, and 2 7s. And then, of course, you have the 3 and the 7. So I have 1, 2, 3, 4, 5, 6 numbers. Here I got 1, 2, 3. What am I missing here? So I got a 3, 7. Oh, of course. I'm actually missing the 3 times the 3, and I'm missing the 7 times the 7. So it's 1, 2, 3, 4, 5, 6, 7, 8 factors, of which 441, and that's not one of the choices. That's not one of the choices. So I'm clearly, how many different positive integers? Oh, and of course the number 1. So how many does that come to? 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. And so that is D. There must be a faster way of doing that. I'll let you think about that one. Anyway, see you in the next video.